capillary rise. We are going to solve for this expression for capillary rise. Now let us draw this diagram first. We are having a container which is filled with some liquid. It is being inserted with some capillary tube, and there will be a rise of liquid in this. Right, because of surface tension, the meniscus or the rise that is going to happen in this capillary tube will be of this shape, and this will make an angle of say theta degree, right? So surface tension is acting at this sigma, is acting in this direction. Now if you want to resolve this, we are known with this angle, theta angle. Now angle of meniscus is theta, and sigma is acting in this direction. There will be two components, that is sigma cos theta and sigma sin theta. This is what is important, to take uh, uh, the components of this force, sigma force, right? The sigma is your surface tension force. You have to resolve this, and then sigma is surface tension force, and angle of contact. Angle of contact is theta between the liquid and the glass. This is now theta is angle of contact. Angle of contact between this curve and the tube. This particular angle is called theta, and sigma is surface tension. Right? Now there are two forces that are acting. One is the force due to surface tension, the force that is acting from this end on the liquid, that is pushing that liquid downward, and another force is the weight of the that has risen in this capillary tube. These two should be equal in a general equilibrium condition. Let us find out the weight of the liquid. Weight of the liquid is W. Weight of the liquid that has risen, that is equal to mg mass into gravity. Now mg is, you can say, volume into density into g. Mass per unit volume is equal to density, and in another term, volume into density is equal to mass into g is gravity. Now this is mg. Now this further can be divided into area into h. H is the height up to which it has risen. Area is the area of the tube into rho into g. Right? Now area is pi by 4 d square into h into rho into g. I hope you are understanding what I am writing on the board. Mg, mass into gravity, is weight. Weight can be written as mg, mass into gravity. Basically, weight is force of attraction, that is with a force with which that object is attracted towards the earth. So that is mg, and mass can be written as volume into density, and volume is further can be written as area into height. Height is the height of the liquid in which that liquid has risen in the capillary tube. Now you can write it rho gh pi by 4 d square. This is weight of liquid. This weight of the liquid is being balanced by this force due to surface tension. Now let us calculate the force due to surface tension. Now this weight is acting downward. Now weight is acting downward, and surface tension is pushing it in this direction. The meniscus is in this direction. The curve is in this direction. We have taken two components, sigma cos theta and sigma sin theta. That component that is balancing the weight will be taken into consideration. So the formula for that will become then sigma into circumference into cos theta. Sigma into circumference into cos of theta. Angle that this meniscus is making is theta, and we have to use cos theta. Any question? Now circumference, the value of circumference will be sigma into pi d into cos of theta. So the equation becomes sigma pi d into cos of or d cos theta. D cos theta. Now we are to calculate height up to which that liquid has risen in the capillary tube. You can compare these two values. These should be equal under equilibrium conditions, right? You compare these two values, that sigma, rho gh by 4 here should be equal to sigma pi d cos of theta. So compare these two values. You have to calculate h out of it. H is equal to sigma pi d cos of theta divided by rho g pi by 4 d square, right? Now in this pi can be divided or cut from top and bottom. Pi d on both sides, it is same d. Small d can be used for here also. So you are left with sigma cos theta or 4 sigma cos theta rho g into d. Rho g into d. As this is in the denominator, this 4 will move to the numerator of the equation. So this is the equation of the rise of liquid in capillary tube. If you have any questions, that is on your screen. Everything is on your screen. You can ask me. Okay. Now, similarly, there is another expression regarding the fall of liquid in capillary tube. Sometimes the liquid is heavier. In time, when the liquid is heavier than water, say there is a fall of liquid in capillary tube. The expression for that is also you have to calculate that also. Now let us calculate that. Expression for capillary fall. Now let us draw this. This will happen in the case of mercury. If you dip a capillary tube in the liquid, mercury liquid, then there will be a fall of liquid level in the capillary tube and a drop of level is like this. This is the H side of which it has dropped in this capillary tube, then this curvature is in this direction, and this is theta angle. There is a there are two types of forces that are acting in this when this is being then when there is a fall of liquid level in the capillary tube. One is the surface tension force that is acting surface tension force, and another force is that force due to which that liquid has fallen below this liquid level. Because of that forces, first one is hydrostatic force. That force is equal to basically weight of the liquid, right? Hydrostatic force is the force which balances the weight. It is equal to almost the weight of the liquid. And second force, that is uh, surface tension force. Right? These two forces has to be in equilibrium to maintain that liquid fall in the capillary. Now, first of all, uh, the fall of force due to surface tension is equal to force due to surface tension. That is equal to sigma into pi d into cos of theta again. Similarly, there will be two components into theta. Is 91 theta. First one is you have to solve this to know this. Then resolve into one will be cos of 90 minus theta, and this is sine of 90 minus theta. So force that we are going to take is cos of theta. If you take sine 90 minus theta is equal to cos of theta over here. You have to take this component. So force due to surface tension is equal to sigma into pi d into cos of theta. Similarly, the other force, that is hydrostatic force, is somewhat similar to that of our weight, which is equal to m into g, and then it can be written as volume into rho into g, and then you can take volume equal to pi by 4 d square into this is area into h is the height of depth into rho into g, and this becomes rho g h pi by 4 d square. Then the fall and capillary will be equal to, and you compare these two values, all in capillary will be equal to pi by 4 d square into h into rho into g should be equal to sigma pi d into cos of theta. From this equation, you have to calculate it is very much similar to that of that we have calculated in rise. Pi by 4 d square into rho into g. Similarly, like as we have done earlier, that it is equal to 4 sigma cos of theta divided by, we will cut pi with the pi and then d with the d. So d rho g. So this is the question for fall and uh, your capillary. Just note down these two formulas. Now we are going to solve for some numericals. If you have some questions up to this, you can ask. So this was the expression that we have done on board. The rise of capillary, that is equal to 4 sigma cos theta by rho gd, and similarly the fall of this is again equal to 4 sigma cos theta by rho gd. The value of theta for mercury and glass tube is 128 degrees. ये आपको that will be given to you. Now you have to calculate a capillary rise in a glass tube of 2.5 mm diameter when immersed vertically in a water and mercury. Take surface tension sigma is equal to 0.0725 for water and sigma 0.52 for mercury. Just in case of water, there will be a rise of water level in the capillary tube, and in case of mercury, there will be a fall of level in capillary tube. You have to calculate H in both the cases. You are given with the specification. Specific gravity for mercury is given as 13.6 and angle of contact is 130 degrees. Right? You have to calculate both these. You can take the, you can write this numerical, and I'm going to do it on board also. So we are going to start with solving this numerical. I am going to do it on board. The diameter that is given to you is D is 2.5 mm, and that can be converted into meters. 2.5 into 10 raised to the power minus 3 meters. Right? Then surface tension is given to you. Sigma is given. The value of sigma is 0.0725 Newton per meter. Then the sigma for mercury is also given, that is 0.52. This is water. This is mercury. It is equal to 0.52 Newton meter. Then specific gravity of mercury. Specific gravity of mercury is mercury is 13.6, and now we have to solve it. Then its density will become 13.6 into 1000. It will become kg per cube. And capillary rise of water. Capillary rise of water. Water can be taken as theta equal to 0. Now H is equal to 4 sigma by rho GD. You can put this value to calculate the value of H. Anybody who has calculated that, you can inform me. What the value of 4 sigma by rho GD and this particular formula that is written on your board for H. The value of sigma for water is given as 4 into 0.0725. Rho is 1000, 9.81, and D is 2.5 into 10 raised to power minus 3. Value to calculate the value of H. Is there anybody who has calculated this? Ashutosh, have you done this?
Hello, sir.
So you just mute your mic. There is some sound that is. You can calculate this afterwards. I am going to tell you the answer for this. That is equal to 1.18 centimeter. The answer will be 1.18 centimeter for water. Similarly, we have to calculate it for mercury also. And that the formula for that is 4 sigma cos theta. Rho GD. 4 sigma cos theta by rho GD. The value of sigma is given to you. In case of mercury, angle is given as 130 degree. Put these values. 4 into sigma for mercury is 0.52, and cos theta is cos of 130 degree. Rho is density that we have calculated 13.6 into 1000. G is 9.81 and D is 2.5 into 10 to the minus 3. Calculate these values.
Sir, minus में आएगी.
Yes, there will be a minus sign also because it is a depression. There will be fall in capillary, the level of water in the capillary. The answer will be minus 0.4 centimeter. You may get 0.004 meter. It is minus 0. हाँ जी
13.6 into 1000 into 9.8 into क्या है सर उसके बाद
9.81
उसके बाद
2.5 into 10 raised to minus 3.
नहीं दिख रहा सर वो कैमरा में.
You are not able to see this?
अब ठीक है सर.
Is it okay now?
Yes, sir.
You can do this numerical. That is written on the board. 0.4 centimeter. Now let us discuss about vapor pressure. Vapor pressure. What is vapor pressure? When a pressure in a liquid falls below vapor pressure. Vapor pressure. What is vapor pressure? When uh, when we boil some liquid and there is a the surface of that liquid and evaporation process starts. That evaporation process is the the evaporation when starts, that vapors or that vapors start forming, as it is clearly visible on the screen also, that if you have a container, you stop heating it, start heating it, then there is a formation of some vapors, and particularly after some time that vapors put some pressure on the liquid below it. That that particular pressure is called vapor pressure. The vapor pressure, the pressure exerted by vapor in equilibrium with its liquid state. When we are having some liquid, we start heating it, then vapors start forming. Then vapors after some time exerts equal pressure on the surface also, right? On the surface of the liquid. That particular pressure is called vapor pressure. Liquid molecules at the surface escapes into the gas phase, and these gas particles create pressure above the liquid in the closed container. So this the vapors that are formed from liquid after heating, then those vapors start uh, exerting some pressure on this liquid, and that particular pressure is called vapor pressure in a closed container. So this is all about this vapor pressure. Then vapor pressure increases with increase in temperature. As temperature increases, the amount of vapor generated at a liquid is container increases. As we heat the system, the more heat increases, the vapor starts, more vapors are formed. As the number of vapors are increased, then the pressure also increases. This occurs because as the liquid gains kinetic energy, the molecules can overcome the intermolecular forces attraction that prevalent in the liquid phase. So when we heat it, the kinetic energy of the molecule starts increasing, and it keeps on increasing, and it exerts more pressure on the liquid phase. Now, there is a term cavitation. If you are understood that what is vapor pressure, cavitation is again a form of phenomena that occurs uh, where there is a pressure, wherever there is a fall of pressure, and pressure falls below vapor pressure, then particular point at that particular point there is a formation of bubbles. That bubbles start moving ahead, and after that they collapse. And they collapse, sound is produced, and this process of formation of bubbles and movement and then collapsing of this bubble is called cavitation. Now let us discuss it in detail. Cavitation is defined as a phenomenon of formation of vapor bubbles. Basically, when you heat something, if you can observe, when you're heating water in some pan, there is a formation of bubble at its surface. Why these bubbles are forming? Because when you heat something, the pressure inside that falls below vapor pressure. There is a formation of vapors over there. That is an air capsule can be said, and that is a cavity, air cavity over there. Vapor cavity is there. Then that bubble starts moving up. Finally, when it reaches its surface, then it collapse. But same phenomena when it occurs in some machinery like a turbine, a pump, when it is moving, when there is a fall of pressure, there is a fall of pressure, and pressure falls below vapor pressure, then there is a formation of cavities or vapors, and then these cavities or bubbles start moving towards high pressure. When they reach high pressure, they collapses. That means the bubbles are broken, and when they collapse, there is a shock wave production. When this shock wave is produced, that if it is a turbine, then it can damage our turbine also. So at this particular phenomena, cavitation is undesirable phenomena. It can erode our material, that is like turbine can be eroded. Pitting erosion is happening because of cavitation. So this is an undesirable process when vapor pressure or pressure inside some instrument or device related to hydraulics. When pressure falls below vapor pressure, there is a formation of bubbles. Bubbles then move towards high pressure. When they reaches high pressure, then they collapse, and the process of formation and collapsing of bubbles, it is so fast that there is a vibration in that particular machine. The vibration is there, then shock wave is produced, then it promotes erosion, and cavitation is an undesirable process. Erosion fitting has happened in some of the parts of the turbine. So cavitation is usually divided into two classes of behavior. In transient cavitation and inceptive cavitation is a process where void or bubbles, a liquid rapidly collapses, producing shock waves. Incipient cavitation is the point where cavitation begins but has not reached a destructive state. Inertial cavitation, when this bubble moves towards high pressure and they collapses over there. When incipient cavitation is that cavitation in which the bubbles are forming but they are not collapsing and they are not non-destructive. So there are two types of cavitation: inertial and incipitive. Is incipient. The incipient is non-destructive and inertial is an destructive cavitation process. Now this is the phenomena of formation of cover bubbles. One is this: initially the bubbles form, then they cavitation, then this bubble moves towards high region, high pressure region. Ultimately, they are going to break, and then this ultimately is broken to two pieces. Then this, wherever this collapses, this particular region is prone to erosion and pitting. Pitting and erosion of exposed surfaces. When there is an exposed surface due to cavitation, there is a erosion of material. Like you can see the image on the right hand side. This is a blade of some part. This the material is removed from the surface because of this cavitation. Uh, as it is an undesirable process, this destroys or damages our parts of different machineries. So large scale cavitation, potential catastrophic failure of valve body and pressure valves, vessel valves. So they may damage our different parts of hydraulic systems. This is again, you can see, this is because of cavitation. This has happened because of cavitation. Localized erosion, sound like rocks, will attack any material. Worse with high pressure. As pressure increases, this uh, cavitation process becomes more worse. So this is all about cavitation and first chapter of your fluid mechanics. So I'm going to stop the recording. Now we are moving to our next chapter, that is fluid statics. Second chapter of your syllabus. Previous chapter was introduction about fluid mechanics, which we have done about viscosity, surface tension, then some of the terms related to that mass density, then special gravity, and then we have done about capillarity, surface tension, all about these things. And last topic of cavitation, right? So the next chapter is fluid statics, in which we study about the fluid that is under static condition and that is not moving. So this chapter deals with that. When a fluid is not in the motion, then we study about this fluid. We call it fluid static. Now this is the basic structure of our fluid mechanics. Fluid is about liquid and gas. Fluid consists of anything that can flow, that is liquid and gas only. Gas are air, helium, argon, nitrogen, and all that. And liquids we come across water, oils, alcohols, etc. Different types of alcohol and oils and all that. Right? Then we study about the compressibility, density, viscosity, and surface tension. When you talk about this introduction, we have studied about compressibility. We have studied about density, which is reciprocal. This compressibility is reciprocal of bulk modulus. Density, uh, mass per unit volume is density. Then viscosity, when two layers move one over the other because of this shearing force, this is viscosity. Then surface tension. We have done up to this. Then the second uh, word is mechanics. In this, we are going to study about statics, dynamics. Statics is stability, pressure, and buoyancy. Stability, pressure, and buoyancy. We are going to study in the statics. Dynamics. We are going to study about laminar turbulent flow and viscous and inner side flow, steady and unsteady flow, compressibility and incompressibility. So this is the structure of your syllabus. There is another term related to mechanics, that is fluid kinematics, in which we consider whether we consider pressure or not, whether we consider for the force whether or not. These all are covered in this chapter. So introduction. This chapter deals with the forces applied by the fluid at rest or in rigid body motion. When you're talking about this chapter, when you are going to learn this chapter, this is the forces applied at when the fluid is at rest. We are going to study about that. In both instances, there will be no shearing stresses in the fluid, and the only forces that develop on the surface of the particle will be due to the pressure. So there will be no movement of the fluid, no sharing of the sharing stresses in there in the fluid. That is, we will not consider viscosity anywhere. We will consider pressure. Now, fluid property responsible for those forces pressure and which is normal force exerted by the fluid per unit area. So, thus our principal concern is to investigate pressure and its variation throughout a fluid, the effect of pressure on the submerged surfaces. So, this chapter is going to basically depend on focusing on. This chapter is going to be focusing on uh, buoyancy, metacentric height, and stability of a ship when it is in the on the surface of the sea. What are the conditions in which that ship will be stable and all that? We are going to study that. Before moving to that, we must know the basics. We are starting with the basics for today. Now, pressure. How to define a pressure? Pressure is defined as force per unit area. Pressure is defined as normal force exerted by a fluid per unit area. We speak of pressure only when we deal with a gas or a liquid. There is no pressure in case of solid. We call it a stress in this particular case. Force per unit volume, force per unit area is stress in case of solids. You all have studied about strength of materials. You have studied about stresses and strains in that subject. Since pressure is defined as a force per unit area, it has units of Newton per square meter. Newton per meter square, which is called as Pascal. You can call Newton per meter square as Pascal also. 1 Pascal is equal to 1 Newton per meter square. That you have to remember. Sometimes in numericals, it is written that the force is 5 Pascals. That is equal to 1 Newton per meter square. The pressure unit Pascal is too small for pressure and encounters in practice. Therefore, it's multiple kilopascals. 1 kilopascal is equal to 10 is for 3 pascals. That again you can use it in numericals. Similarly, megapascal, 1 megapascal to 10 is for 6 pascals are commonly used. So this slide is going to be very helpful when you are to convert some units of pressure from one to another. Pascal to Newton meter, Pascal, kilopascal to Pascal, and megapascal to Pascal. So other pressure units commonly used in practice, especially in Europe, are bar, standard atmospheric pressure. So 1 bar is equal to 10 raised to power 5 pascals. So sometimes in numericals it is written as uh, pressure of 5 bar is in use. So then how to convert into pascals? Then you are just multiply it with the 10 raised to power 5. And 1 bar is equal to 0.1 megapascal and 100 kilopascal. 1 atmospheric pressure, 1 atm is equal to 101325 pascal. You are not going to get uh, this unit in your books 1 atm because most of the units are in either in bar, either in pascal. So actual pressure at given position is called absolute pressure. You may have heard about the absolute pressure of this particular process is this. So actual pressure, we call it absolute pressure. It is measured relative to absolute vacuum, and it is the base is taken as vacuum is absolute vacuum is taken as base, and you measure pressure from that is called absolute pressure. Most pressure measuring devices, however, are calibrated to read zero in the atmosphere, and so they indicate the difference between the absolute pressure and the local atmospheric pressure. Generally, when you fill airs or you measure pressure with some gauge, it is indicating you the difference between absolute pressure and the local atmospheric pressure. So gauge the pressure that is gauge is representing it as the difference between atmospheric pressure and this absolute pressure and not the absolute pressure. The pressure below atmospheric pressure are called as vacuum pressure. When a pressure falls below atmospheric pressure, we call it a vacuum pressure as measured by vacuum gauge that indicates the difference between atmospheric pressure and the absolute pressure. Absolute gauge and vacuum pressure are all positive quantities and are related to each other by this. You have to remember this also. Now gauge pressure is equal to absolute pressure minus atmospheric pressure. And vacuum pressure is equal to atmospheric pressure minus absolute pressure. This is how to calculate. If you are asked to calculate gauge pressure, then you have to subtract atmospheric pressure from absolute pressure. And if you are asked to calculate vacuum pressure, then you have to subtract absolute pressure from atmospheric pressure. So thermodynamic relations and tables, absolute pressure is almost always used, at most used throughout this course. Generally, we are going to use absolute pressure as a word again and again, and that is pressure from atmospheric pressure to, vacuum pressure to the actual pressure. This absolute pressure is, it is measured absolute from vacuum pressure, not from atmosphere. In thermodynamic relation tables, absolute pressure is always used. So this is the diagram that is representing what is vacuum pressure, what is absolute pressure. Now, this is the absolute vacuum pressure. You can call it zero pressure. And this is this line, the dotted line is representing atmospheric pressure. Then the gauge pressure, when you check, you are checking for the pressure in your tires. That particular gauge that is used, that is giving you value from this line to this line. And absolute pressure is from this point to this point, right? So this is a diagram that represents the different types of pressure. So pressure at a point, pressure is compressive force per unit area. It gives the impression of being vector. However, pressure at any point in a fluid is same in all directions. That is, it has magnitude but not a specific distance, thus it is a scalar quantity. So pressure can be considered as a scalar quantity. There is no direction of it. It occurs in equal in all directions. Thus can be demonstrated by considering a small wedge shaped fluid element that was obtained by removing a small triangular wedge of fluid from some arbitrary location within a fluid. Since we are considering the situation in which there are no shearing stresses, the only external force acting on the wedges are due to pressure and weight. Now, this is a very important law that we are going to start with. This is Pascal's law. It states that the pressure intensity remains same in all directions. It states that the pressure or intensity of pressure at a point in static fluid is equal in all directions. Right? For simplicity, the force and the x direction are not shown, and the z axis is taken as vertical axis so that weight acts in a negative z direction. Now let us solve this on board also. Let me share you.